So good evening, good morning, good afternoon, wherever you might be. Thank you for joining us. What I'm going to say is tonight, because I'm on the East Coast of the US, so it's late at night for me. But welcome to our Terra Talk featuring our guest speaker, Dr. Chip Fletcher, who joins us from Hawaii. My name is Cynthia. I'm an Axolotls instructor for Group 6, and I'm stepping in for Greg tonight, who has taken the week off to go skiing with his kids. So Chip is a great friend of the Terra community who has been giving guest talks since our very first cohort. And his talks are considered one of the highlights of the course by many previous fellows, Greg included. Greg loves Chip's talk. And it's a pleasure to have him here with us. So Dr. Fletcher is the interim dean of the School of Ocean and Earth Sciences and Technology at the University of Hawaii, at Manoa, and he's the former chair of the Honolulu Climate Change Commission. Chip's teaching and research focus on climate change, coastal communities, resiliency, and natural coastal systems. He has received a number of teaching, research, and community service awards, and together with his students, he has published over 100 peer review articles and 3 textbooks. We're really excited to have Chip here with us tonight. One last comment from me before we get going. We'll be doing questions through Slido, which I think is what you all used for the welcome session. I'll drop that link in the chat, but if you want to ask any questions, do ask them on Slido and not in the Zoom chat. So welcome, Chip, and thanks for being here.
Thank you, Cynthia. Thanks, everybody, for joining. I know many of you are at odd hours of the day or night, and I appreciate your eagerness to learn about climate change. Let me share screen and get started. What I'd like to talk about today is not only climate change, but also simultaneous global problems. I would label them crises, in fact, of biodiversity loss, pandemics, and human inequality. So to get started, let's develop a fundamental understanding of the problem of climate change. Sunlight may enter Earth's atmosphere. If it hits a bright surface, a white surface, it will be reflected back out to space. It won't do any work in terms of warming the atmosphere. But if it hits a dark surface, such as open ocean water, tree canopy, continental land, it will be absorbed. And as we all know, that surface will warm up, and then that surface will radiate heat. So during a warm afternoon, if you walk across the black surface of a parking area, you've got heat radiating. This heat is in the form of thermal infrared radiation. It's just a fancy scientific name describing the frequency of the energy. But that particular frequency, infrared radiation, actually is very important to a very thin layer of gases that exist in only trace amounts, but are very powerful at trapping that heat. And these are known as greenhouse gases. They reside in the troposphere, which is just the lower 6 miles or 10 kilometers of the Earth's atmosphere. The troposphere is the layer of the atmosphere that we live in. And these gases will trap this heat that would otherwise escape to space and then re-radiate it back down to Earth's surface, or in all directions, in fact. So what's going on here is that these gases are heating Earth's surface a second time. And that is what develops our warm climate. Without this natural greenhouse effect, the average temperature on Earth's surface would be below freezing, and life as we know it wouldn't exist. So a natural greenhouse effect is very important to the habitability of our planet. But we have been burning fossil fuels and releasing carbon that had been stored in Earth's crust for millions of years. We are mining it and releasing it to the air, which is causing more carbon dioxide to build up in the atmosphere. And that carbon dioxide is warming the air to the point where we're also getting a feedback effect, which amplifies the warming. You all know that as the air gets warmer, it gets more humid. And that humidity is actually water vapor, which it turns out is the most powerful greenhouse gas, the most powerful naturally occurring greenhouse gas. So through burning fossil fuels and releasing carbon dioxide and methane and nitrous oxide, we warm the air, which triggers a rise in humidity, and that water vapor increase will trap even more thermal infrared radiation, driving more warming, and thus we have what's known as an amplifying feedback effect. This is a critical aspect of anthropogenic climate change, or what we call global warming. Water vapor accounts for about 36 to 70% of the total greenhouse effect, but it's the carbon dioxide that we have released that accounts for almost 80% of the additional global warming, the anthropogenic global warming. So this is why carbon dioxide is tracked and carefully monitored as a major pollutant causing climate change. Another reason for this is because carbon dioxide has a long residence time in the atmosphere. Once it's released through burning fossil fuels, carbon dioxide will reside in the atmosphere for centuries to millennia. And we need to physically remove it in order to counteract the warming effect that it creates. There's more going on than just carbon dioxide and water vapor. We have a group of other gases and particles that influence the trapping of heat in the atmosphere. I won't dwell on these, but I will mention to you this last one on the list here, reduced aerosols. It turns out that as we replace fossil fuels with cleaner forms of energy, solar, wind, and other forms of non-fossil fuel energy, we are actually cleaning up the air. Now, that has tremendous health benefits for us, but it allows more sunshine in. And we call this global brightening. And as we allow more sunshine in, of course, that triggers additional global warming. So this is the carbon dioxide record measured here in Hawaii at Mauna Loa Observatory. And when it was first being measured, carbon dioxide was accumulating annually at less than 1 part per million per year. Today, it is accumulating annually at more than 2 parts per million per year. So the rate of accumulation of CO2 in the atmosphere is accelerating, and it continues to accelerate. We've currently reached between 415 to 420 parts per million. That is the concentration of CO2 in the air. This is more than 50% greater than the natural concentration, the pre-industrial level of less than 300 parts per million. More than half of all industrial carbon dioxide emissions have occurred since 1988, when NASA scientist James Hansen testified before the US Congress that climate change was real, it was happening, we could see the effects, and that it was the result of fossil fuel burning. 40% of the CO2 that we emit today will still be in the atmosphere in a century, and about 20% will still be there in 10,000 years. So, although I know you've heard of reducing fossil fuel emissions, you may not have heard very much about the need to draw down CO2 from the atmosphere. This is a fundamental pillar of climate change activity, which is to remove CO2 from the atmosphere using activities, human activities, and we'll get into that. We have a new problem which has developed, and that is methane emissions. Methane emissions have set record highs each of the past 3 years. Methane's responsible for as much as 1/3 of near-term global warming, and it's 25 times more powerful at trapping heat than carbon dioxide. It doesn't have the long-term residency time that carbon dioxide has, but it's far more powerful. We can measure the isotopes of carbon that are being released in this methane. And it tells us that the source of this methane is microbe activity in wetlands and in thawing permafrost. These are natural systems responding to global warming. And so this drives the question, is accelerating methane nature's response to global warming? And can we control it? This may be an early indication of nature taking off on another amplifying feedback effect or reaction to the warming that we've caused, potentially out of our control. The jury is still out on that, though, so it's a major worry, but we don't have a final answer yet. This is the record of Earth's surface temperature since 1880. This data is collected by the US NASA, our space agency. You can see a strong acceleration from the 1970s. There was strong acceleration of global warming taking place leading up to World War II. But then after World War II, the world economic engine turned to manufacturing. This marked a fundamental shift from an agrarian global society to a manufacturing society in the industrialized nations. Manufacturing from the 1940s up through the 1970s was not generally controlled by clean air laws. And so the emissions from manufacturing blocked out a lot of sunlight, and for several decades there suppressed global warming. But in the 1970s, the United States, the European Union, which hadn't yet been formed, but European nations and other industrialized nations began passing laws to clean up factory emissions, clean air laws. And with the reduction of these aerosols coming out from manufacturing, we saw global warming take off again as more sunlight was allowed to warm Earth's surface. Last year came in as the 5th or 6th warmest year on record. And each of the last 8 years has been hotter than any year prior to 2015. You can see that this record has a lot of annual variability. Typically, these cool years tend to be either volcanic eruptions, which have emitted aerosols that will temporarily block sunlight, or they will be years characterized by La Nina. La Nina is a Pacific process where strong trade winds in the southern hemisphere tend to bury heat from the air into the ocean. We get what's known as the Western Pacific warm pool expanding around the Philippines and around the equator, and that is transferring heat from the atmosphere into the ocean temporarily because of strong trade winds. You notice we also have warmer than average years. These years, generally speaking, are El Nino years, which is the opposite of La Nina. El Nino is when the trade winds die and we get heat coming out of the Pacific Ocean into the atmosphere, which leads to a temporary warming or a warmer than average year. Now, we've had a persistent La Nina state for the last several years, but that's coming to an end. And this northern hemisphere summer, we may be looking at the beginning of an El Nino. And so this temporary stability in global temperature over the last 8 years or so may come to an end, and we could see another jump up in temperature as we move into an El Nino phase. This is not unusual at all. In fact, it's come to characterize this record. You can see that there's a sort of a stair-step characteristic to it. We have a number of years where there's no net warming, then a jump up, then another set of years with no net warming, then another stair step, stability, jump, stability, jump. This has become a characteristic of the climate change situation. And lastly, I want to point to the title here. We have now warmed on the order of 1.1 to 1.3 degrees Celsius above the pre-industrial average temperature. This may not strike you as very much warming, but I urge you to consider the analogy of your human metabolism. A low-grade fever is what we're looking at in human metabolism forms. If you look at this in terms of Fahrenheit, we're talking about 2 degrees Fahrenheit. That is enough of a temperature to keep you home for the day. You don't feel like getting out of bed. And should that low-grade temperature persist for weeks, you'll actually begin to experience severe organ damage. There are a number of systems in the world that are extremely sensitive to small changes in temperature. Our body temperature is one of them, and so is Earth's surface environment. So these are analogous. This is a map of the temperature change relative to the average. So if we have an average temperature change of, say, 1.2 degrees Celsius, everything in red has warmed more than that, and everything in blue has warmed less than that. And what's obvious here is a couple of fundamental patterns. Continents are warming faster than oceans. This puts bread baskets and human communities at risk. Although the global average is 1.1 to 1.3, in the Northern Hemisphere summertime, we're looking at 4 degrees Celsius, 5 or 6 degrees Celsius warming taking place over that 3 to 4 month period, and 5 to 6 degrees Celsius warming during heat waves. This can drive temperature regionally beyond human capacity to endure the heat. Also notice that the Arctic is warming 4 times faster than the global average. Remember, the North Pole is an ocean covered in ice. Today, that ice reflects sunlight, but as it retreats and exposes dark ocean water, we are fundamentally changing the reflectivity of the planet, exposing more dark ocean water, which will absorb sunlight and then re-emit heat, which will be trapped by greenhouse gases. So Arctic amplification is actually driving the instability of the Northern Hemisphere jet stream. The jet stream is a river of wind at high altitude that runs through the temperate latitudes. And as the Arctic warms faster than the tropics, the gradient, the temperature difference driving those winds is reduced, and those winds move slower, and the jet stream becomes sluggish, and you get large meanders in the jet stream. And these meanders lead to Arctic air coming down much further south than it would normally, and tropical air punching much further north than it would normally. So we have wintertime record-setting cold snaps and summertime record-setting heat waves. This is one of the reasons why we have dramatic extreme weather happening, because the jet stream is becoming destabilized because the Arctic and the tropics are looking more and more alike, more and more. The temperature difference between the two of them is not as great as it used to be. And it's that temperature difference or gradient that drives wind circulation. And so, of course, we're seeing heat waves, drought, flooding, hurricanes, and all sorts of risks to human society, human security. I'm sure you were aware last week, the last report from the Intergovernmental Panel on Climate Change was released. It was called the Synthesis Report. The IPCC, Intergovernmental Panel on Climate Change, publishes assessment reports, or ARs. This was AR6. The last assessment report was in 2014, 10 years ago, basically. And there are several reports in each AR. We have a physical report on the physical basis of climate change. We have a report on mitigating climate change. We have a report on adapting to climate change. This is the synthesis of all those. And it tells us the requirements to stop warming at 1.5 degrees Celsius. It updates us. Greenhouse gas emissions must peak before 2025. Emissions must be cut by 60% within 10 years of that. Carbon removal is now essential to limit global temperature rise to 1.5 degrees Celsius. Climate impacts on people and ecosystems are more widespread and severe than expected, and future risks will escalate rapidly with every fraction of a degree of warming. More than 3 billion people already live in areas that are highly vulnerable to climate breakdown. Half of the global population now experiences severe water scarcity for at least part of the year. Some climate impacts are already so severe that they cannot be adapted to, leading to losses and damages. Climate finance for both mitigation and adaptation must increase dramatically this decade. And those who emitted the least amount of greenhouse gases are paying the heaviest price. Climate change and efforts to adapt and mitigate it will exacerbate global human inequity should we fail to ensure a just transition. Weather extremes are increasingly driving displacement of people in Africa, Asia, North, Central, and South America, and the South Pacific. What we do in the next few years will determine our fate for millennia. Recognizing the problems associated with global warming, the United Nations Framework Convention on Climate Change holds annual meetings known as COPs, or Conference of Parties. During the Conference of Parties in 2015, which was held in Paris, the world's nations agreed to a climate accord to stop global warming before it reached 2 degrees Celsius and to pursue efforts to end warming before it reaches 1.5 degrees Celsius. Shortly after that report, or after that meeting, a report came out in 2018 examining the question of what will the world look like at 1.5 degrees Celsius. And we learned about hot extremes, heavy precipitation, drought, sea level rise, species loss and extinction, damage to the ocean, increased disease and storminess, decreased food and water security, decreased human safety, and increased human inequality. And with this report, 1.5 degrees Celsius became the new international target for stopping global warming. To give the world a 66% chance, or a 2/3 chance, of limiting warming to 1.5 C, climate science suggests a carbon budget of 280 gigatons can still be emitted. This is just 7 years of current emissions. So let's ask the question, what is our progress on stopping warming at 1.5 degrees Celsius? On the bottom axis, we have time to mid-century, and on the vertical axis, we have carbon dioxide emissions. The black line is the history of emissions leading up to the COVID recession. In 2020, with the COVID pandemic, emissions dropped 5.4%. But then in 2021, with the rise of a vaccine and the release of stimulus funding from the world's governments to stimulate the economies around the world again, we saw emissions take off again. In fact, they rose 5.7%, setting a new record, beating the old record in 2019. Last year, emissions rose another 1%. Keep in mind, emissions have to decrease in order to stop global warming, and this is the pathway. We need to see a 60% reduction in emissions by 2035, and we need to reach net zero. In fact, the new report says we need to reach net zero by 2040. So I need to update my slide here. Under the Paris Agreement, the world's nations have announced their nationally determined contributions, or NDCs. These are pledges to reduce their emissions nation by nation. These promises would put us on a pathway of warming to about 2.5 degrees Celsius. However, there's a difference between promises and actual investments and policies. On the ground, the policies of the world's nations actually take us to 2.8 degrees Celsius, or potentially over 3 degrees Celsius by the end of the century. This represents a fundamental problem known as the gap, the difference between promises and policies. And every year, the United Nations Framework Convention on Climate Change, typically in November, prior to that year's COP, comes out with what's known as the GAP report. And this latest GAP report is called the Closing Window. This came out in November of last year. And it says that models indicate that emissions need to be cut by 45% by 2030, and that current commitments will increase emissions by over 10% by 2030. The report also said that there is no realistic pathway to stopping warming at 1.5 degrees Celsius. This was the first time that had been acknowledged. This was sort of well-kept secret, or afraid to say in public by most climate scientists. We realized really 20 years ago that stopping at 1.5 degrees C was going to be a miracle. Now we're finally seeing in print confirmation of that. But there's more bad news. During the COP 2 years ago in Glasgow, Scotland, a report came out from the Washington Post revealing that on average, emissions around the world are underreported by 23%. And this reveals one of the problems with the United Nations approach. There are, in fact, no penalties for lying. There are no penalties for a nation failing to live up to its promises or pledges. And because so many nations are failing to live up to their pledges, there's no public embarrassment involved in any particular nation failing to do so. But there's a deeper problem here, which is not well known. So to get at this next problem, let's take a look at the sources and sinks of carbon dioxide. On average, every year, 89% of the CO2 that humans emit comes from burning fossil fuels, and about 11% comes from deforestation and poor soil treatment during agriculture. If you leave soil open to the air, the carbon in that soil will oxidize, and fields of agriculture will turn into sources of carbon dioxide. This happens when you don't use cover crops and when you engage in deep plowing. There's a difference between industrial agriculture and regenerative agriculture. Regenerative agriculture treats soil as a storehouse, a sink of carbon, but regenerative agriculture is not practiced widely around the world. Once this CO2 is released, 48% of it on average goes into the atmosphere and traps heat, causing global warming. About 29% of it is absorbed by plant photosynthesis on land. And 26% of it dissolves into the ocean, leading to ocean acidification. This terrestrial biome conducting photosynthesis is unfortunately beginning to fail just under the small amount of warming that's happened already. So let's look into that. So plants engage in photosynthesis, which removes CO2 from the air. Plants also engage in respiration, which releases CO2 and water vapor to the air. Photosynthesis has a heat limit. And when it warms beyond this thermal limit, photosynthesis sharply declines, but respiration continues to increase. In other words, plants become net emitters of carbon dioxide. With continued emissions, models are suggesting that carbon uptake by plants on land may be degraded by nearly 50% in only 20 years. This effect is also not accounted for in the nationally determined contributions to the United Nations Framework Convention on Climate Change. I've got a couple of papers here. I'll just pull out this one quote from this particular paper in the Proceedings of the National Academy of Sciences. It says, numerous studies suggest that a variety of ecosystems are operating at or near their thermal thresholds. What we're talking about here is we are on the brink of the collapse of photosynthesis should warming continue unabated. All we need to do is look at the Amazon basin to get a grasp on this problem. The Amazon contains more than half of all tropical rainforest, but it is logged, mined. There's hunting, deforestation for agriculture, damming of the many rivers. There is drought and tree mortality from heat and wildfire. Over the past decade, the Amazon lost 1/3 of above ground biomass. And between 2010 and 2019, the Amazon basin released 18 billion tons of CO2, but only sequestered or drew down 15 billion tons. So it's now likely that the Amazon is a net source of greenhouse gas. This is a map of human impact in the Amazon. The darker the red, the greater the human impact. All of this dark red area to the south and southeast is area that has been deforested for farming. But the major type of farming taking place is actually growing soy and maize or corn for cattle feed. And this is how what you eat relates to the climate change problem. Because there's a growing hunger for beef around the world, Brazil is taking advantage of this. Argentina has been taking advantage of this. Many South American countries and also many African countries are growing the food that's needed to feed cows in order to provide the strong desire for beef, which we see around the world. But carbon loss from the rainforests is taking place across the entire planet, not just in the Amazon. So from 2001 to 2005, the entire tropical rainforest belt of the planet released about 1 billion tons of carbon per year. But then 10 to 15 years later, it was releasing twice that, almost 2 billion tons of carbon per year. 82% of this carbon loss from tropical rainforests was because of agriculture. And this paper concluded the strategies to reduce forest loss have not been successful on a global scale. And you can see the increase in carbon loss taking place between these two panels in South America, Central Africa, and Southeast Asia. Strong increase over that 10 to 15 year period. Most of this is due to agriculture. The world is growing hotter, especially on land in the summer. So there is what's known as the wet bulb temperature. This is a measure of heat and humidity. And the reason we measure humidity is because when it's humid out, a thin layer of moisture on our skin prevents our body metabolism from releasing heat to the air. And this impedes our cooling. And 35 degrees C wet bulb temperature actually marks the limit of humans' ability to survive, our physiological limit. This paper tells us that extreme humid heat overall has more than doubled in frequency since 1979, and that 37% of warm season or summertime heat-related deaths can now be attributed to climate change around the world. This data comes from 732 locations in 43 countries. There's now paper after paper warning us about heat-related mortality, emergence of heat and humidity too severe for human tolerance, escalated global exposure to compound heat and humidity extremes with warming, business as usual emissions will lead to super and ultra extreme heat waves in the Middle East and North Africa, deadly heat waves projected in the densely populated agricultural regions of South Asia. These papers continue to come out. This paper was published by the Proceedings of the National Academy of Sciences in 2020. It's called The Future of the Human Climate Niche. And it tells us that today, these black areas in the Central Sahara Desert represent less than 1% of the land surface. And these are locations where it's literally too hot for human existence. A perfectly healthy person in the shade with abundant water availability will not make it to the end of the day. These conditions represent the edge of human existence. And on our current pathway to nearly 3 degrees Celsius, we're going to see these conditions expand to nearly 1/5 of the land surface. Everything in the dark brown diagonal hatching will be equivalent climate conditions to the black areas in the Central Sahara. And as you can see, it's basically the entire region of the tropics, from Northern Australia through Southeast Asia, India, the Middle East, North Africa, South America, and Central America. In fact, starting at today's global warming temperature of about 1 degree Celsius, for each additional 1 degree C, we can expect to see 1 billion people displaced from their current homelands. And ultimately, at 3 degrees Celsius, we're looking at 1/3 of humanity displaced from where they currently live, on the move, looking for new locations in which to set up a life for themselves. We also have food and water impacts besides extreme heat. We're currently withdrawing fresh water from our continental aquifers faster than nature can replenish it. In the continental United States, we are pulling 17% more water out of our aquifers than is naturally replenished every year. China is pulling 22% more than natural renewal. India, 52%. And the Middle East and North Africa, more than 1,000% faster than nature can replenish this water. By 2050, demand for water is projected to grow by more than half. Already, 1/4 of humanity faces a water crisis every year, with 17 nations under extremely high water stress, meaning they're using almost all the water they have every year. And in 2018, this city, Chennai, in India, of over 10 million people, literally ran out of water. 4 massive reservoirs dried up because of the late arrival of the monsoon. We saw a similar situation developing a year later in 2019. Food is also at risk. You may not realize that when the air has more CO2 in it, the soy, wheat, corn, and rice that we grow is less nutritious. Food staples under higher CO2 have up to 13% less protein, zinc, vitamin B complex, and iron. The protein is actually replaced by carbohydrate. So these foods actually become more sugary. And this is simply because of more CO2. But as we saw with deforestation, there are multiple human impacts when it comes to food shortages. So today, global wheat provides 1/5 of all human protein on average, but the annual yield of wheat is threatened by drought, flood, and this problem of higher CO2. By mid-century, the demand for wheat is projected to increase by 60%, but the actual yield is projected to decline by 15%. This is a recipe for food shortages, price spikes, and riots. We already have developing around the world the problem of insufficient food. By 2050, an additional 300 million people will be malnourished because of the CO2 effect and the reduction of micronutrients in the 4 food staples. An additional 1.4 billion women and children are likely to also have anemia or iron deficiency because of this micronutrient problem with higher CO2 in the air. All of this adds up to a global security problem, displacing communities and leading to climate migration. The US Council on Strategic Risks has issued a report which says even at scenarios of low warming, each region of the world will face severe risks to national and global security in the next 30 years. Higher levels of warming will pose catastrophic and likely irreversible global security risks over the course of the 21st century. At the same time that we are damaging human society through climate change, we are sacrificing the natural world to our insatiable consumption patterns. There is a pervasive human-driven decline of life on Earth, which is pointing to the need for transformative change. Since 1970, per person consumption has increased by 59%, and global economic activity has grown by 400%. Much of this growth has come at the expense of the natural world, which is increasingly managed to keep up with rising demands for food, energy, timber, paper, minerals, and more. A lot of this is due to beef agriculture. Since 1970, food crop production increased 300%, and half of all agricultural expansion has come at the expense of forests. More than half of deforestation is to raise cattle and the grain to feed them. 50% of all habitable land and 2/3 of all freshwater use on this planet is for food production. Over 80% of farmland is used for livestock, but it produces only 18% of human calories. Cattle and the grain they eat use 1/3 of available land surface on this planet. 16% of all available fresh water. 1/3 of worldwide grain production goes to feed cows. And producing beef generates 100 times more greenhouse gases than plant-based agriculture. %86 of all land mammals by weight are now either cows or humans, or a combination. Of all birds, 70% of all birds on this planet are chickens and other types of poultry. Human overconsumption and population growth and intensive farming has destroyed 69% of vertebrate wildlife over the last 50 years. This loss of biodiversity is linked to the spread of disease. We've now entered the era of pandemics. There have been 335 new infectious diseases in recent decades. 75% of these are zoonotic, which means that these diseases jump from animals to humans. Ebola, HIV, malaria, West Nile, anthrax, encephalitis, Zika, SARS, MERS, COVID-19, and many, many others are examples. These are called spillover events, where microbes carried by animals cross into humans through contact. There are 4 general venues for these spillover events, and the first is habitat loss. Roughly 1/3 of new zoonotic diseases are directly attributed to deforestation and habitat loss. About 50% of the world's original forests have now been eliminated. And globally, we cause a net loss of about 10 billion trees per year. Less than 3% of Earth's land surface is considered faunally intact. That means that the animal relationships for mating, seasonality, predator-prey relationships, alteration to the environment by animals, all of these have been thrown out of natural equilibrium. And much of the loss in the animal kingdom has been from our killing and hunting of apex predators. By removing apex predators, we've allowed the explosion of small mammals and other types of vectors which carry disease into our communities. We also have extreme weather events. Flood, wildfire, and heat displace both humans and pathogens as well as vectors, bringing them in contact to each other at a time when human immune systems are weakened. Disease is always a major problem following disaster events. And the expansion of disease-carrying organisms. The tropics are expanding. Mice, mosquitoes, ticks, deer, and other carriers are moving into human communities. These small mammals can live cryptically, very successfully in human communities. Rats, mice, and many forms of small mammals can live in a hidden lifestyle in our communities and carry disease. The 4th venue for disease transmission is through concentrated animal feeding operations or industrial agriculture of poultry, pigs, and cattle. It's very common to put hundreds of animals or thousands of poultry into a warehouse, and disease will run through this community. But when disease runs through a community in a natural setting, the natural evolution of the virus or bacteria cannot afford to increase its virulence. It cannot afford to increase the degree of fatality. Otherwise, it will run out of hosts. So in a natural setting, diseases are limited from evolving into extremely pathogenic organisms. But when you're in a industrial agriculture situation, every time an animal dies, they remove the dead animal and they put a new animal, living animal in. And so the diseases can develop mutations into strains that have extreme levels of virulence, extreme levels of pathogenesis. There are strains of avian flu that have 70% mortality rates. We keep these animals alive by pumping them with antibiotics under these situations. And nearly 2/3 of drugs important to human medicine in the US are actually sold for this purpose, to keep animals alive in agriculture situations. And of course, this is what leads to bacterial resistance, which is another major problem that we have. The rise of super staph or superbacteria or viruses that resist our medical treatment. Disease, environmental damage, and climate change form an amplifying feedback with human inequality. The global human population has been crippled by an era of Western domination and colonialism. We see unstable governments that have been destabilized by colonialism, attempting to come back into a degree of self-determination, and they are saddled with this crippling history of Western domination and colonialism. Disadvantaged groups suffer disproportionately under climate change, disease, and environmental damage. And this results in even greater inequality. The ratio between the income of the richest and poorest 10% on this planet is now 25% larger than it would be in a world without global warming. So we are continuing to stratify society, and the lower levels of our human community do not have the resources to recover from an extreme weather event or to recover from the stresses of climate change before the next extreme weather event or the next stresses of severe climate change come on top of that. So there's no resilience. The only resilient human population these days are the developed nations. And every year in the Northern Hemisphere summertime, I watch as the headlines roll by with more heat waves, more severe drought, threats to human breadbaskets, extreme weather situations, and we're also beginning to put at risk the resilience of even the developed nations at this point. The richest 10% of the global population owns over 3/4 of all global wealth. The poorest 50% owns just 2% of global wealth. This is the history of carbon dioxide emissions since the 19th century. And this is what we have ahead of us in order to stop global warming at 1.5 degrees. Zero emissions by 2040. An additional 15 years if 2 degrees Celsius is our target. Emissions must peak by 2025. We need a 60% reduction by 2035. and we must remove CO2 from the air beyond this century. This infrastructure is nowhere in evidence. This decade, 2020 to 2030, is the most pivotal decade in the entirety of human existence and will determine our fate for millennia. The recent report came out with 12 key solutions to mitigate climate change: retire coal plants, invest in clean energy and efficiency, retrofit and decarbonize buildings, decarbonize cement, steel, and plastics, shift to electric vehicles, increase public transport, biking and walking, decarbonize aviation and shipping, halt deforestation and restore degraded lands, reduce food loss and waste and improve agricultural practices, eat more plants and less meat, and create social tipping points. Society must recognize the immoral nature of fossil fuels. Reduce, reuse, and recycle. In fact, we are engaged in a real energy transition. This graph began in 1850, and it shows global sources and sinks of carbon dioxide. In red are fossil fuels and land use changes. Our historic emissions over the last century or half a century averaged about 3% per year. But over the past decade, our emissions have plateaued to about 0.5% per year or less on average. We now need to reduce our emissions and go into negative emissions. After 200 years of fossil fuel expansion, we are at a turning point in the global energy system. Projections of future warming today are 25 to 30%, 35% lower than they were just 5 years ago. We no longer talk about 5 degrees Celsius warming. We're talking more about 2 to 3 degrees warming. Global carbon emissions growth has slowed. At least 18 countries have managed to cut their emissions consistently for more than a decade. Last year, the world spent $1.4 trillion transitioning to clean power. This is the same amount that was spent producing oil and gas. This is the first time that renewable energy investments equaled fossil fuel investments. Renewable energy is getting cheaper. The world is set to add as much renewable power in the next 5 years as it did in the past 2 decades. Renewable energy will account for 38% of global electricity over the next 4 to 5 years. Between 2010 and 2019, the costs for solar energy fell by 85% and wind energy fell by 55%. Solar is now 33% cheaper than natural gas. In 99% of cases, it is more expensive to keep coal-fired power plants in the US running than to build an entirely new solar or wind energy operation nearby. In 2022, the US generated more electricity from renewables than from coal. This is the first time on record. Investment is pouring into renewable energy at a record rate. Global energy demand growth will now almost entirely be met by renewables. By 2025, global emissions should reach a peak and then either plateau or decline. Economic growth no longer requires rising emissions. Jobs in clean energy will more than double by 2030 from 6 million to 14 million. And energy efficiency improvements have delivered huge gains. New countries are passing climate laws. 91% of the world's GDP is covered by countries with net zero targets. However, ambition needs to accelerate. There's no credible pathway for stopping at 1.5 degrees C, but we still have a chance of stopping warming by 2 degrees Celsius. A central scenario for modeling by British Petroleum, which is a highly respected source for economic and energy scenario modeling. Global carbon emissions peak in the 2020s, and by around 2050 are only 30% below 2019 levels. Of course, they need to be 100% net zero. So we are still not acting fast enough, although the transition is real. And I will close with this quote from Lord of the Rings. We don't choose the time we live in. The only choice we have is how to respond. And I want to thank you for your time. And I know I've gone over, but I will stick around and answer all your questions as long as you have them. So thank you very much.
Thank you so much, Chip. That was great. Let me start with a couple of questions here. I think a few you answered along the way, but maybe this is the best one to start off with. Do you think the IPCC is being too conservative in their scenarios, and should it consider negative feedback loops more closely?
I don't know that negative feedback loops are the problem. If you're referring to amplifying feedback loops, that's the proper terminology. And yes, the IPCC is far too conservative. Their modeling, in fact, makes a number of assumptions that are becoming less valid, especially when you consider underreporting of emissions and the beginning collapse of photosynthesis. I did not mention that Arctic permafrost is now a net source of carbon, and other global systems are beginning to change in response to the warming that's already happened. So yes, I think you're right there. The IPCC really does undersell their story. A major reason for this is because they have a policy that every nation on Earth must agree to the wording in their summary reports. And of course, we have a number of nations which are driven by fossil fuel economies. And so when you look at the original science language and the final report language, it's highly watered down and does not express the urgency that the scientists are trying to communicate with their original language.
Great, thank you, and thanks for the question, Mark. I'm just trying to find, sorry for my question. There's a question, I've seen this question come up in a few different ways, but I'll ask it in this way. If the Amazon is now a net emitter of carbon dioxide, why is halting deforestation one of the 12 key solutions?
Not helping deforestation, helping stop deforestation. Was I missing the word stop in there?
Why is halting? Sorry.
Halt yeah. Deforestation. Okay. We need to halt deforestation. We need to stop deforestation. And we need to allow reforestation and afforestation. So reforestation is the regrowth of forests in areas that have been deforested. Afforestation is the spread of canopy into areas that did not previously have canopy.
Right. So I guess their question is, if the rate of photosynthesis is declining in large rainforests, so let me rephrase this in the other way it came out.
I got it.
Yeah,
right.
yeah.
Well, it hasn't reached zero yet, and the projections were a reduction by half in 20 years. So, assuming that we continue on the energy transition, we certainly need all the natural infrastructure, the nature-based solutions we can to sequestering carbon, to pulling carbon out of the air, and also to preserving the soil. When you look at a forest, the vast majority of the carbon is actually in the soil. 60 to 80% of the carbon is in the soil. And regrowing the forest to protect that soil and to rejuvenate the carbon storage of the soil is critically important. Areas of deforestation not only lost the plants, but the soil itself is now becoming a carbon source as carbon just streams out of the unprotected soil.
Great, thank you. I saw a question, I think you touched on this briefly at the end of your presentation, but I'll still ask that 1.5 sort of target, is that unrealistic at this point? And should we be shifting that benchmark?
Well, you're suggesting that we reduce our ambition by shifting the benchmark. No, we can't afford to reduce ambition. We have to accelerate ambition. Even though 1.5 may not be realistic, by reducing ambition, we're going to miss 2 and we're going to miss 2.5. So, the reduction of photosynthesis, the lack of 1.5 being a realistic target, these were not, I did not give these to you as an excuse to lay off of the problem. They are meant to invoke urgency on your part. They're meant to invoke, in fact, some degree of panic and some degree of grief. I want you to experience the emotional impact of potentially losing the natural functions of this planet. That's not an excuse to walk away from the problem. It's supposed to be motivation to solve your grief, right? Optimism is embedded in action. We can't succumb to the grief of losing this planet. We must become active, and through our actions, such as you signing up to take this course and me talking to you, we find optimism.
Okay, I'll take a couple more questions. That seems like such a great point to end on, Chip. I like that motivational goodbye. I'm going to ask a couple more. Some of these aren't super climate science specific, and we'll deal with those in lab. But this is such a tricky question. But do you have any thoughts on sort of the most impactful thing we can focus on? Perhaps scaling that down to the group of Terra fellows that are here. Like, what's the most impactful thing people on this call could do?
There is no sector of the human socioeconomic realm that is not important. From art to literature to music to physics, chemistry, engineering, every single element of our human activities can play a massive role. And all of you have a comfort zone and a skill set which should allow you to find that place, allow you to find that activity which brings you optimism. So, are you an economist? Are you a basket weaver? Are you a dancer? What is it that you like to do that gives you happiness? Identify the bridge, build the bridge, identify the connection between that skill set and that natural orientation that you have, and mitigating climate change, reducing biodiversity loss, and solving the problems of human inequality. So they're all important. I'm not going to rank them. You rank them for yourself and your personal comfort zone. That's where I think we can all play a role.
Great. And with that, great. Thanks, Chip. And with that, I think we'll wrap up for the night, because some of these other questions we are going to talk about in lab. So we'll save those. But I really appreciate you being here, Chip. I appreciate everyone being on the call. And I echo what Chip says. The fact that you're all here is great. The more people we have looking at this, the faster we're going to get there. So thank you all.
Yep. Thank you, guys. And yes, the slides will be available.
Perfect. Thanks, Chip. Thanks so much.
Okay. Take care. Bye-bye.
Thank you.